Alright, so 8.8. Um, if you're just joining us, we just had a brief discussion how everything we've done so far on our calculus class has been dealing with integrals and derivatives that have met the conditions of being continuous over a certain interval. Therefore, we were able to perform all the derivatives and all the integrals that we have been dealing with in the class. But now, what happens when you don't meet those requirements? What happens when you have discontinuities? And that's what we're going to deal with today. Okay? Alright. So, let's talk about what the definition of an improper integral is. So, here we go. So, the definition of improper integrals . And I just realized there's a whole bunch of writing, and why would I rewrite it when I have it done? So switching here. So here we go. The definition of an improper integral with infinite integration limits. So there's a purpose. I know that you thought it was kind of random for me to throw limits in between integration, and that's because we're going to need to use limits in our integration when we're dealing with improper integrals. Okay? So you have three different scenarios. So if you're watching the video, go ahead and pause the video so you can copy down the information, and then we will talk over some examples, and that will be pretty much our notes for the day. Okay? So we'll go ahead and pause the video. Alright, so hopefully by now you've already written everything down, so let's kind of discuss each one individually. So right now we're still going to talk about things being continuous, so we still don't have discontinuities itself. But let's talk about when these are situations when you are approaching not a constant, you're approaching a limit that goes to infinity per se. So if you have something that goes from a constant to infinity, then you have to then rewrite it as a limit. Okay, you're gonna get rid of this infinite limit here, and you're gonna substitute it by I typically choose the letter B. You can choose anything. Okay, but if you change this, that means that, remember, the whole existence of an integral is because of a limit. You're taking a limit. You guys recall that? So what I've done is I kind of gone back to the basics, and I've rewrote this as a limit going towards infinity, and then I just replace that with the letter that I chose, and you should have no problem then integrating using these two limits here. But when you get the answer, you got to take the limit as it approaches infinity of whatever your integral was. Okay? Yes?
So we would get a value for that integral.
Yes.
And then, so we would just, the limit of that would just be
the actual value of the integral. Yes. As you can see, number 2 is the exact same thing, except this time you're going from negative infinity. So you're doing the same situation where you're replacing by a random variable here. Typically I call it a, and we're doing the same thing. We're going to rewrite it as a limit. So we're going to go back to the basics. And last and not, but one of the most important in my opinion is when you go from negative infinity to infinity, you're going to have to replace both of them. So you're going to have to introduce a couple variables here, so 3. Okay, so first of all, you want to break it up into from negative infinity to a constant, and then plus from that constant to the positive infinity. That constant, you choose whatever you want it to be. This one is one of the ones that you're actually going to choose a value for it. Okay, so you're going to plug in a number for it, and I'll show you an example of what that is. But once you have this, you guys realize that then it's going to be a repetition of rule 1 and rule 2. Right, so this would be like rule 1, and this would be like rule 2, and then you do the exact same thing for each one. Cool? Now, here's something that's important about this whole concept of going from negative infinity to infinity. Because you're going to break this up into 2, if either one of these diverges, then the entire thing will diverge. Which means, remember, convergence versus divergence. Convergence means that you're going to actually obtain an actual tangible value. So like, let's say the result will be like 2 or 5 or 100, but you're actually reaching that value. For something to diverge means that you're going to get a result of infinity, meaning that you're never going to approach an actual value. Remember that infinity is not a quantity, it is a concept. Cool? Alright, so then let's go ahead and try then some examples. And just like with anything we do in this class, I hope you've noticed I do this on purpose. We start with something easy. We start with something basic, right? I want to make sure that you start with something easy, build your confidence up, and as we move along, they're going to get more difficult. The other things that I want to achieve through this lesson as well, and you're going to notice it on the homework, is there's a lot of things for you to remember in this class. Agreed? Especially as the AP exam is coming. So what I did with the homework in this, I chose a lot of problems that are going to help you review a lot of your integration techniques. Okay, so you're going to, in here, you're going to practice, like I know for sure, integration by parts is going to come up while we're doing this process in your homework. U substitution is going to come up. Trigonometric substitutions are going to come up. Just simple trigonometric integrals that you should know. So I'm trying to help you practice while at the same time learn the new concepts. Cool? Alright, so the first example we want to try looks as follows. So we're going to go an integral from 1 to infinity of 4x to the negative 4th power dx. Okay? Alright, what do you guys think? So this is just a relatively simple problem to begin with. We're running into the situation where this is improper because you have the infinity, right? So how first you do what? You got to rewrite it as a limit, right? So this is going to become the limit as what approaches what? You just got to pick a variable. I'm going to typically just use the letters A, B, and C. So typically I call that B. So let's call that B approaches infinity of the integral from 1 to B of 4x to the negative 4th power dx. So we rewrote it as a limit. Now for the moment, now if you kind of block that off, now this has become a problem that we've done before, except that you have a variable, but there's nothing wrong with that. You can still integrate it, right? Okay, so if we integrate this, we can just use the simple power rule. Agreed? So the limit as b of, we're going to add 1, right? So x to the negative 3, and we're going to divide by that number, so negative 4/3. Agreed? And because it's a definite integral, we're going to evaluate it from b to 1. Cool? Alright, so then the limit is still going to be hanging out here. We haven't applied it yet. We want to simplify things out. So remember, when you have a definite integral, you want to input these values in for x, right? So then the first one becomes negative 4/3 b to the negative 3, right? Minus, we got to plug in the 1 value, right? So 1 to the negative third power is just 1, agreed? Times negative 4/3, negative 4/3, right? Okay, so then you just want to clean this up a little bit before you take the limit. So the limit as b approaches infinity of 4 over 3b to the third, right? And it's going to be negative. And then this negative times negative makes it a positive, right? So plus 4/3. Alright, once I'm here, what do you guys think? This has just become a simple limit problem now, right? But you have to remember your rules when you evaluate a limit as it goes to infinity. What do you guys think? Remember that you don't have to do this, but you could break this up into two limits, right? But if you really think about it, if you put infinity there, that means that this is going to be infinitely large. And the bigger and bigger this gets, that means that you're approaching. So this would just be 0. And the limit of any constant is just what? The constant itself. So the answer would be 4/3. Because you have an answer, this limit converges. Cool? Alright. Next example. Example number 2. And I'm actually going to flip the page because this one will require a little bit of space. Or it's up to you how you want to do it. I just want to have it all in one page for you. I'm going to flip the page. Example number 2. Let's say you have the limit. I mean, not the limit. The integral from negative infinity to positive infinity of 4 over 36 plus x squared dx. Cool? Alright. What do you guys think? What should I do first? We could find the vertical asymptotes, right? Do you guys definitely know that there will be vertical asymptotes here because you have a rational function, right? You could sketch this out so you know how this looks like. You could also just begin by rewriting this, and then you can start from there. So either way, I don't care. So if you want to sketch this out just so you have an idea what this looks like, or if you want to just kind of begin with the math, either or, okay? I'm just going to go ahead and break this up, and then we can talk about the graph here in just a second. So if I break this up, what would you break this up into? So this is going to become the following, right? So the integral from negative infinity to what? Some c value of 4 over 36 plus x squared dx plus what? The integral from where to where? C to infinity of the same thing. Agreed? You guys with me? Now, the problem when you do something like this is that you actually have to have a value for C. This is one of the ones that you can't just leave C in. You have to have an actual value for it. How you choose your C could be very beneficial to know what the graph looks like. Okay? So before I even think about where I'm going with this and graphing this, think about this for a moment. Forget about this being a definite integral. Pretend this was an indefinite integral. Agreed? If you take the integral of that, what would it be? It's one of the ones that we have to have memorized. It's arctangent, because you have an a squared, a perfect square there, a perfect square there, right? So it's going to be one of those arctangent, right? So what does this look like? What do you guys think? So where do we have asymptotes for this? Let's start there. Every pi over 2, right? Agreed? That's for tangent, right? So the tangent, remember, it's not every pi over 2. It's every n pi over 2, right? Agreed? So where n is an integer. So you would have one at pi over 2, 3 pi over 2, 5 pi over 2, etc., 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 right? So what do you guys think it's a good value to choose for C? What's right in between negative pi over 2 and pi over 2? Because we definitely know that exists, right? And why pick a value that's going to make more difficult? Right? 0 is going to be something that's going to cancel things out for you, right? Anytime you can use 0, use 0. Unless, obviously, that's where your asymptote is, and you're going to have to pick something else. Cool? Alright, so now, this means that you're going to have to apply rule 2 and then rule 1. Agreed? Okay, so this one, we need to rewrite it as a limit. Agreed? So this is going to become the limit as a approaches negative infinity of the integral from a to 0 of 4 over 36 plus x squared dx. Plus, this is going to become the limit as b approaches infinity of the integral from 0 to b of 4 over 36 plus x squared dx. You guys with me so far? Okay. the limits you always don't have to worry until the end, right? So just keep dropping the limits. So the limits as a approaches negative infinity of. What is the integral of this? Well, we already talked about this being arctangent, right? Agreed? Who remembers the rule? What do I do with this 4, by the way, first? It's a constant, right? Can I just pull it out? So it would be like you'll be in the front. So then you would have 1 over 36 plus x squared. The rule for arctangent says what? One over a, right? So times 1 over what's your a value in this 6 times the arctangent of what? Which in this case would be x over 6, right? And then we're going to evaluate that from a to 0. Agreed? That's one of the limits. Plus, limit as b approaches infinity, and it will be the exact same thing, agreed? Of, I'm going to go ahead and simplify this out. 4 times 1 6 is going to be 2/3, right? So 2/3 arctangent of x over 6, but this time we're going from 0 to b. Cool? Alright, so if we then expand this out, this becomes the limit as a approaches negative infinity of 2/3. If you plug in 0, that would be arctangent of 0, right? So what angle has a tangent of 0? So wouldn't that just go away? It would be 2/3 times 0, right? Minus 2/3 times the arctangent of a over 6. Agreed? And that's the first limit. Cool? Plus the limit as b approaches infinity of, this time we're going to plug in the b first, so 2/3 arctangent of b over 6 minus, well, don't we run into the same situation? The arctangent of 0 is 0 times 2/3 is just 0, right? Cool? Okay, so then that means we have the limit as a approaches negative infinity of negative 2/3 arctangent of a over 6 plus the limit as b approaches infinity of 2/3 arctangent of b over 6, right? Alright, now this has become a limit problem. What do you guys think? Not necessarily, no. You have the right thoughts. Why do you think it's undefined though? It diverges. Okay, so here's what's happening. So you're saying you're plugging in this negative value here, right? So if you plug in this negative, the bigger and bigger it gets, right? What happens to this value right here? It just gets to a bigger number, agreed? Or in this case smaller because it's a negative, right? Okay. Well, as it is increasing, you remember that there's an asymptote, right? And that's why you're saying that it's undefined, agreed? But where is that asymptote present? Well, let's go back to what tangent looks like. Agreed? And that's what it looks like, right? So you're saying that as it is approaching negative infinity, so you're going that way, right? And you keep going and you keep going and you keep going and you keep going, you keep going, you keep going, you keep going, you keep going. What are you approaching? So it's a negative pi over 2. So this would be negative pi over 2.
Are you in the interval at -5 or 57?
I'm sorry?
Are you just in the interval at -5 or 57?
Yeah, because think about it. This applies. I know, like, this is where it gets a little confusing with this. I know that you're from -pi over 2 to pi over 2, but if you really think about it, you're never going to reach -pi over 2 or pi over 2, so you're really satisfying the condition that you are truly approaching negative infinity. And that's just where calculus sometimes becomes a little mind-blowing. You're like, wait, what? But think about it. You're never, like, you keep going towards infinity. You keep going, you keep going, you keep going, you keep going. You're never going to reach the pi over 2 or the -pi over 2, so you're continuing. So you are meeting the condition of going towards infinity on both directions. Cool? So because you're approaching that asymptote, so that means you're approaching the left side, which is the -pi over 2 times the 2/3, right? Plus, then what will be the limit of this side? 2/3 times what? What are you approaching on the infinity side? The positive pi over 2. Therefore, you have negative times negative, cancel out the negative, so pi over 3 plus pi over 3, so 2 pi over 3. Does it diverge or converge? It converges. And these are the type of limits that and integrals that get a little bit more confusing to understand because of this whole concept of divergence and convergence and thinking as the limit approaches infinity, etc. Okay? Alright, we have one more example and we're done. Cool? But there's more rules. Alright, are we good with this one? Alright, here's the next one. What if you have an improper integral with infinite discontinuities? Okay? You're going to have another 3 scenarios. And I'll explain what this means here in just a second. I'll draw an example of what this looks like, okay? So, alright, so let's kind of talk about what's happening here. Let me just kind of give you a sketch differently. So, this time we're going to talk about situations such as, let's pretend you have, I don't know, a graph that looks something like this. I don't know, I'm just going to make this up. Let's pretend it's going up in that direction and there's an asymptote right there. And then there's an asymptote right there. Okay? But then I ask you to evaluate an integral from, I don't know, let's pretend this is the number 1, and this is 2, 3, 4, 5, 6, right? And I ask you to evaluate it from 1 to 6. So then at that point, it's like I'm asking you for this. Agreed? But as you can see, this time you have a definite integral, right? Neither one of them is infinite continuity in between those two values. You won't know this from the beginning. You're going to have an idea of if there is a discontinuity here or not. Okay? So, I know that throughout the year you kind of went away from the definition and you just integrated everything without really thinking about whether or not it met the requirements of being continuous versus not being continuous. You're going to have to make sure that you do. Because if it doesn't, you're going to have a discontinuity in between and you're going to have to apply one of the rules that we talked about here. So, if, for example, you're dealing with a situation where you're going from A to B, right, and B happens to be a discontinuity, right, as you're approaching B from the left-hand side, you can rewrite it as this, right? If A happens to be your discontinuity, you can write it as you approach it from the right, okay? But the problem becomes once you have it right in the middle, like the example that I just showed you, you're going to have to break it up into 2 different integrals just like we did before. But now your C value has to be definitely at the value where you have the discontinuity. Cool? And really everything else just works the same way that we've been doing. You can use the limits, etc., turn it into a limit. The thing about this third one is that, again, if you're taking the integral of this function from A to B, and you're breaking it up into 2 because of this continuity in between, if either one of these diverges, then this entire thing diverges. Cool? Alright, so let's go with an example. Where are we? Example 3. Okay. Let's say you have the integral from 0 to e squared of the natural log of x to the third power dx. Cool? Alright, the first thing I would do is before I even grab this, or before I even really attempt this, I want to think about what the natural log looks like, the graph of natural log looks like. Do you guys remember what the graph of natural log looks like? Can you take the natural log of a negative number? Can you take the natural log of 0? No. So wouldn't that mean that you would have an asymptote at 0? And then it would look something like that, right? Okay. Do you see that how now we have a problem? From the interval from e0 to e squared, we have a discontinuity. So in reality, we don't have a closed interval from 0 to e squared. We don't. We have an open interval from 0 to e squared. Therefore, failing the requirements of taking the integral, right? Which means that we're going to have to use these new rules. We're going to have to rewrite this thing. Agreed? Okay. So, one of the things I want to do before I begin integrating this thing, are you guys okay if I bring this 3 to the front? So I don't have a power. So then I'm going to rewrite this as 0 to e squared of 3 natural log of x dx. You guys with me? Okay. What do you guys think then? Can I go ahead and integrate this thing as it is right now? No. You're going to have to rewrite it as what? You're going to have to rewrite it as a limit. You have to replace this here because it's not continuous there. Okay? So we're going to rewrite it as a limit as a approaches that value. But does it approach it from the left or does it approach it from the right? From the right. Agreed? So from the right, you're approaching it, right? Of a to e squared of 3 natural log x dx. We're good? Okay. We're going to ignore this limit part for a moment. Now we have a definite integral that we can definitely integrate. Okay? 3 natural log of x dx. I need to integrate that. What do you guys think? What's that? Take the constant out. Do you guys agree? Can I take the constant out? Cool. I can. Sure. So if I do that, so let's say the limit as a approaches 0 plus of 3. Cool. Do we know the antiderivative of natural log of x? We don't. We know if it was 1 over x, the antiderivative would be natural log of x. But we don't know an antiderivative of natural log of x. So that means we're going to have to do what? We can try u substitution, right? We can let u be ln x, but then du would be 1 over x, which is not present. So when that fails, you have to use substitution by parts. Liate. Okay? What are you going to get let u be? Liate, L is the first letter, which is the log, so ln x, right? Which means that du would be 1 over x dx, right? And what would dv be equal to? Well, what's left? Just dx, right? And if you integrate dx, you get the v is what? X. You guys with me? Okay, so then the limit as a approaches 0 from the right of 3, and then I'm going to put this right here. So it's uv, right? X ln x minus the integral of u dv, right? So v du, my mistake, sorry, v du, right? So v is x, and du is 1 over x dx. and we're still going from a to e squared. Agreed? We're good so far? Sorry, it's another bracket there. Cool. Alright, so then we have the limit as a approaches 0 from the positive side, from the right side, of 3 times x ln x minus, what's x times 1 over x? 1. So wouldn't that be that the derivative would, the integral would be what? X, right? From a to e squared, right? You want to attempt to finish this problem on your own, please? Try it, see what you get. Okay, so pause the video, I'll finish the problem here, and then I'll show you the response here in just a second. Alright, so what I did here, guys, and you didn't have to do this, but I went ahead and distributed the 3 just to make my life easier, not to have to worry about that 3 later on. So I distributed, and then I plugged in e squared and a. So when I plugged in e squared, here's what I get. 3e squared natural log of e squared minus 3e squared. Minus, now I'm going to plug in the a. And I always use parentheses so I don't forget that that negative has to be distributed in. Okay. Now here is the key, and the more algebra you remember, the easier things become. Remember that when you take the natural log of e, that's just 1, and it just leaves you with the power. So that means that you have, this becomes 2 right here. Okay, because remember the power rule says that you can bring this 2 to the front. So it's like saying 2 times 1. So then you have 2 times 3 squared, so that's 6 of them. And then you're taking away 3 of them. That leaves you with 3 of them left. Okay? And then minus, I said the 3a ln a. And then I'm going to distribute that negative again, and it becomes a positive 3a. At this point, what I did is I broke this up into 3 different limits. You don't have to, I just did it so I can stay organized. Okay, the first limit would be limit of a constant, agreed? And the limit of a constant is just a constant, right? Then the second one becomes minus the limit of 3a ln a. I recognize that if I plug in 0, this becomes 0, but if I plug in 0 there, that would be infinity, and 0 times infinity, that's an indeterminate form, which tells me that I could use L'Hopital's rule. So what I did is I rewrote this 3a ln a as 3 ln a over 1 over a. Okay? And then plus the limit of 3a, again, I plug in 0 for that, and that goes to 0, right? So then I'm left with 3 squared minus the limit as a approaches 0 of 3 over a divided by negative 1 over a squared. I've already went ahead and took the derivative. Okay, so the derivative of 3 ln a is 3 times 1 over x, right, which is 3 over, well in this case, I'm sorry, a, not x, right, so 3 over a, and the derivative of 1 over a would be a to the negative 1, so you will subtract 1 and multiply by that value, right, so then it's negative a 1 over a squared. Cool. This is already 0, so here I am, and then I realized that this is like fraction divided by fraction, so I went ahead and simplify that. Keep, change, flip. It reduces to be negative 3a. Cool? So then I still have this constant here and this 0, but as the limit of a approaches 0 from the right, if you plug in 0, 3 times 0 is just 0. So it equals to 3e squared minus 0 plus 0, which is 3e squared. Therefore, this converges. If you don't show this step, right here, and this was on a free response, you would not get credit. You gotta show that you use L'Hopital's rule. You don't have to write the word L'Hopital's. They can identify that you used it, but you have to show that you used L'Hopital's rule to obtain that became 0. Otherwise, they will then assume that you thought that the natural log of 0 was 0, which is an incorrect concept. Cool? Alright, other than that, that's all I got for you guys today. That will be improper integrals. I will make sure that I upload everything as far as homeworks, notes. You should have your quizzes back. You can use all of that material so that you can get ready for this test. Test will be on Tuesday unless something happens, but hopefully that's what it will be scheduled to be. Cool. If you need my help with tutorials, I will be available during the weekend. Just contact me through Remind. Take a picture of a problem that you're working on. As soon as I can get to it, I will get to it and I'll send you back. On Monday, I'll be here early in the morning if you want to come in for tutorials. Same thing on Tuesday. in the morning, and I will even stay on Monday after school if you need me. Okay? Just communicate with me. Sweet. All right, that's all I got.